So if you're involved in designing or building, say, a modern hospital, you're walking this tightrope, right?
Oh, absolutely.
On one side, you have dangerous electrical overload, and on the other, millions of dollars in just wasted copper.
And the line between them really comes down to how well you understand assumed electrical usage.
Exactly. And that all comes down to one massive book.
The National Electrical Code, NFPA 70.
Today, we are going to do a very focused deep dive into the 2023 edition of the NEC. We're going to zero in on Chapter 2.
Yeah.
We really want to understand the very specialized rules for calculating electrical loads in healthcare facilities, and that means we have to crack the code on demand factors.
Yeah, and the mission here for you listening isn't just to read the rules, it's to get the philosophy behind them.
Right.
Why does the code make one assumption for an operating room and a completely different one for, a regular patient room?
Right.
We need to decode the exact volt-ampere threshold so you walk away knowing how to avoid both wasted capacity and catastrophic failure.
Okay, so let's set the stage. The NEC is, well, it's enormous.
It's intimidating.
It is. But it's organized pretty logically. It kind of takes you from general principles in Chapter 1 through wiring in Chapter 3, all the way to special cases like hospitals in Chapter 5.
And our focus today is Chapter 2, wiring and protection. It's foundational.
So this is the basics for everything.
It is, but it has these, let's call them specialized pockets.
Yeah, right.
We're going straight into one of those.
Yeah.
Part 6, which is all about calculating loads in healthcare facilities.
Okay, but before we get to the numbers, we have to talk about something you mentioned. The rooms. Categorization.
Yes.
The entire calculation we're about to do hinges on how that space is defined. So why is this category 1 through 4 thing so critical?
You've just hit on the most important piece of context. The code is all interconnected. The notes right in our section point you back to Article 100 for the definitions of these categories. You can't size the wire if you don't know the room type. It's that simple.
So if we go look at Article 100, how do we translate that into, plain English?
You can think of it in terms of risk. What happens if the power fails?
Okay.
Category 1 is your most basic non-critical space. Think waiting rooms, maybe some offices.
Yeah.
Category 2 is like a general patient room. Power failure there isn't good, but it's probably not going to be an immediate life and death situation.
Okay, so the risk is increasing. Where's the line where it gets really serious?
That's Category 3. This is where procedures happen. Exam rooms, labor, and delivery rooms. Losing power here could interrupt critical care.
And Category 4 must be the highest risk.
That's right. Category 4 is your ICUs, operating rooms, neonatal critical care. Any area where an electrical failure could mean immediate loss of life.
That makes perfect sense. The math has to reflect that jump in risk from a waiting room to an ICU.
Precisely. So with that in mind, let's look at the rules for using these special demand factors in Section 220.11 now. There are a few key criteria.
What are they?
First, these calculations only apply to receptacle loads that are figured out according to another section, 220.14 H&I.
Okay, a cross-reference.
Right. Second, and this is a big one for hospitals, the circuits supplying these outlets cannot exceed 150 volts to ground.
Wait, hang on. Why that limit? 150 volts. Why is that so important in a hospital?
Oh, it's a huge safety firewall. It's all about fault protection and grounding. In those critical Category 3 and 4 spaces, you often have isolated power systems.
To prevent shock.
Exactly. To minimize the risk of electric shock to a patient who's hooked up to all sorts of monitors, limiting the voltage to 150 volts to ground drastically reduces the potential fault current. It lowers the risk of microshock or macroshock to both patients and staff.
Got it. So if you meet those safety rules, then you're allowed to use these special demand factors. So let's talk about what a demand factor actually is.
A demand factor is, it's like the electrical engineer's version of tax brackets.
Ah, okay, I like that.
You don't design the whole building assuming every single outlet is maxed out at the same time. That would be insanely expensive and wasteful.
We need massive wires.
Massive everything. So the code gives you this calculated diversity factor, the demand factor. It's the percentage of the total load that's assumed to be running at any one time.
Which lets us size our feeders and panels efficiently. You don't waste money on copper you don't need, but you're still completely safe according to the code.
Exactly. It moves the design from a kind of theoretical worst case to a statistical reality. But that reality changes a lot depending on the room category.
Okay, let's start with the less critical spaces then. Category 1 and 2, that's table 220.1101. Walk us through it.
So for these general patient areas, the code hits you hard right away. The first 5,000 volt amperes or VA of receptacle load gets a 100% demand factor.
100%. So no discount at all to start. They assume everything is running.
None. They force you to account for that initial load. But after you pass that 5,000 VA mark, the code starts to acknowledge diversity. The load from 5,001 VA up to 10,000 VA gets a 50% demand factor. So the assumed usage is cut in half for that slice.
And then comes the biggest drop, which seems to really define these spaces.
Yes. Any remainder over 10,000 VA, the demand factor just plummets. It goes down to 25%.
25%. That's a huge drop. So if I'm designing a wing full of general patient rooms, once I get past 10,000 VA, the code is basically betting that 75% of my outlets are sitting idle at any given moment.
That's the engineering assumption, yeah. These are seen as having transient intermittent loads. A vacuum cleaner, a temporary monitor, not constant heavy use.
Okay, so hold that 25% number in your head.
Right, because now we're moving from the general patient rooms into, well, the deep end, the critical care zones.
We're transitioning to table 220.1112. This is category 3 and 4, the ICUs, the operating rooms. What's the most obvious difference here?
The initial 100% threshold. It's completely different.
How so?
In these critical areas, the code assumes much heavier, sustained usage. The first 10,000 VA or less is subject to a full 100% demand factor.
Wow. That's double.
Yep.
Double the initial full load. The code is saying you have to assume twice as much critical gear is drawing power at the same time right from the get-go.
Absolutely. The sustained load assumption is much higher, and the drop-off, it's nowhere near as steep.
What is it?
For category 3 and 4 spaces, the entire remainder over 10,000 VA is subject to a 50% demand factor.
Okay, so let's put that together because this is where the safety and the money is. In the general rooms, you drop to a 25% assumption pretty quickly.
Right.
But in the critical rooms, you hold at 100% for twice as long, and then you only drop to 50%. You never go lower.
That 50% floor is the key insight.
Mm-hmm.
The code is demanding that even after the initial load, you have to assume at least half of the remaining outlets in a critical care space are active.
And that means?
Larger wires, bigger panels, and maybe a much larger generator for your emergency power supply to that part of the hospital.
So if an engineer messes up and calculates a Category 4 operating room using the Category 2 table,
It could be a disaster.
that 25% factor could lead to a catastrophic overload right when life support or an anesthesia machine is plugged in and running.
That is the exact risk.
Yeah.
In a surgical suite, you could have monitors, a robot, lighting, suction,
Mm.
all drawing heavy power simultaneously. You can't assume the same diversity you'd find in a regular patient room.
Huh.
That higher assumption, that 50% floor, forces the system to be robust.
This has been a really amazing breakdown. We've gone from this, huge, complex document all the way down to 2 very specific tables that can dictate the safety of a multi-million-dollar project.
It just reinforces that you have to read the code for the philosophy behind it.
Yeah.
These tables aren't arbitrary. They're based on decades of data about how power is actually used in these high-stakes environments.
And as we wrap this up, I keep coming back to where we started. The categorization of the space itself. The whole calculation, the 25 versus 50%, the 5K versus 10K, it all depends on whether you call a room category 2 or 3.
Everything hinges on it.
So the question to leave you with is this. What specific measurable criteria, things like life support or how invasive procedures, do the code writers use to draw that hard line between a category 2 general room and a category 3 procedural room? That's what justifies such a drastic difference in the electrical demand.
Understanding that definition is the real first step to safety.
We'll catch you on the next deep dive.